The magnitude of the electric field vector E at any point is proportional to the density of the electric field lines surrounding that point. That is, the electric field is strong where field lines are close together and weak where they are far apart. So let's take a look at the electric field of a positive charge. We will draw some electric field lines representing the strength of the electric field and the direction of the electric field in space. Remember, for positive charges, the electric field lines point radially away from the charge. And I should add, that's if the positive charge is isolated in space, if there are no other charges that contribute significantly to the overall electric field. So here is the electric field lines of a positive charge. The strength of this electric field is depicted in this picture at any point in space. For example, for regions in which there are a large number of field lines, the electric field is stronger. Let's look at a region right here. I'm going to take a rectangular area. Notice in this rectangular area, there are 3 electric field lines passing through. Now notice as we move this rectangular area up, the field lines space farther and farther apart. In that area, it gets less and less dense with field lines. And now notice there's a point in which there's only one field line. The density of that electric field is much less further out than it is closer up, even looking at it from the side. So we have 2 electric field lines, and notice the density. In this small, compact region of space, and I am going to just do this right here. If we track that region of space, we would say the electric field is stronger here than out here, or even just a little bit away, because there are fewer field lines in that immediate region. So this is why we can use this electric field line model to indicate the strength, the relative strength of an electric field. So that's why we could use this electric field line model to indicate the relative strength of an electric field in space. The greater the density of electric field lines, the greater the strength of the electric field. And notice for this positive point charge, since the electric field lines spread out the farther away we go, we know that the electric field for this positive charge decreases with distance. Let's look at it for a negative charge. I'll draw the negative charge at the center of an electric field. These electric field lines indicate that the electric field is along a radial axis with respect to the charge, where the charge is at the center. Remember, for negative charges, the electric field lines point radially toward that negative charge that is isolated in space. Also remember that electric field lines point in the direction of a positive test charge. So what that would mean is if we were to place a positive test charge somewhere in space, like let's say right here, that positive test charge would experience an attractive electric force due to the negative charge, and that attractive electric force is due to the electric field. And remember, the electric force is proportional to the charge placed in the field times the electric field. If we look at the density of the electric field lines for this negative charge, notice once again, the density of charges increase the closer we get to the center of this field. Here, the electric field has 3 lines going through this particular area. And notice just moving a little bit away, now we have no lines. That doesn't mean there's no electric field anywhere else in that rectangle I drew. Remember, this is just a model. There are an infinite number of electric field lines. But what this model indicates for us is it gives us a symbolic representation of how the strength of the electric field varies with distance. Here, the field lines spread out the farther away we go, so the electric field of this negative charge weakens. If we had an arbitrarily shaped electric field, let's say similar to what we have depicted in the diagram, and here we'll say we won't know the relative strength, or we won't know the source of the electric field, rather. We don't know if this source is due to a collection of positive charges or a collection of negative charges. All we know is that the electric field in this region of space looks like this. Well, from this diagram, I could see that the electric field is weaker up here and stronger down here. I know that because the number of field lines per unit area increases as we move down the screen. So for example, if I just draw an arbitrary area shape like that, notice right there in that region of space, we have 1 field line. Now again, there's an infinite number of field lines. This is just a visual model for the relative strength. And as we move further down, notice now we have 2 field lines in a particular region in space. Now we get to a point where there's 3 field lines, so this field is getting stronger. And now we have 4 field lines, so the field is getting stronger. The number of field lines starting or ending on a positive or negative charge respectively is proportional to the magnitude of the charge. The field lines never cross, since the electric field at any point is a vector with a unique direction. So here I have depicted 2 positive charges. One positive charge has a magnitude of 4q. The other positive charge has a magnitude of 8q. Now remember, the number of field lines drawn is totally arbitrary. We're just using it to indicate relative strength. So from this diagram, we see that the charge on the left, the 4q, has half the strength as the charge on the right. The reason why the 4q charge has half the strength is because it has half the number of electric field lines. So let's say I depict our 4q like this, and let's depict our 8q charge like this. One thing to remember is that the density of field lines in space corresponds to the relative strength of the electric field at that region in space. That means just by looking at the density of field lines, we could see that the 8Q charge has more field lines per unit area than the 4Q charge. And you can see that just by drawing a representative rectangle there. Here I have, in this region of space right by the charge, 3 electric field lines. In the same region of space, for the 4Q charge, I just have 1. Now, that doesn't mean that this 8Q has 3 times the strength as this 4Q at that region of space, because remember, this is just a model. But how we're going to interpret the number of field lines is like this. The number of field lines is directly proportional to the strength of the electric field at a given region in space. So that means if you double the number of field lines, you double the electric field. If you quadruple the number of field lines, you quadruple the electric field. The 8Q has 8 field lines, the 4Q has 4 field lines, so the 8Q has twice the strength at any location as the 4Q charge. The shape of a net electric field in a region of space due to more than one charge is influenced by the types and positions of the charged particles. Here, we have an electric field due to an electric dipole. An electric dipole is just an arrangement of a positive and a negative charge. Each charge has the same magnitude of charge, it's just that one is positive and one is negative. As you see in the diagram on the left, that electric dipole having a positive and a negative charge produces an electric field that looks a lot like that if you were to map it out with your test charge. Notice how the electric field is curved. Notice how the electric field lines start on the positive charges and end on the negative charges. And depending on where you are, the net electric field, which is what this diagram depicts, the net electric field of both charges, would look like this, and in most regions of space will be curved, except for on a line directly connecting the center of those 2 point charges. In this diagram on the right, these are 2 positive charges. Those 2 positive charges would produce an electric field that looks like this. Notice the electric field lines begin on each positive charge and point away. But because of the contribution of each charge at every point in space, if you had your test charge to probe the electric field, you would get a shape for the net electric field looking like this. Because your test charge can only detect the net electric field at a point in space. It won't be able to detect the individual positive charge on top or the individual positive charge on the bottom unless each of those were shielded somehow. Your test charge is going to detect the net electric field at any point in space. And for a 2 positive charge arrangement, it would look like what you see. If we had 2 negative charges, it would look just opposite of that. For me, the interesting thing about these fields is it kind of looks like they're pushing away from each other. So it's a reminder to me when I take my electric field probe to sketch the electric field vectors, the net electric field at any point in space. To me, even my sketch suggests and reminds me that 2 like charges repel. Now notice how I'm drawing the electric field lines ending on the negative charge. The reason why they're drawn ending on the negative charge is because, once again, if we had our positive test charge would experience a force that would be directed tangent to the electric field vector, or the electric field line at that point. Now let's look at our dipole arrangement. The number of field lines starting on a positive charge is equal to the number of field lines ending on a negative charge. Notice that these two charges have an equal magnitude of charge. So the number of field lines leaving the positive charge is equal to the number ending on the negative charge, and there is the same number of field lines radiating out in space. Let's say we had a charge configuration where there's an unequal amount of charge. So one charge is going to be negative 2q, and the other charge is going to be positive q. Negative 2q has twice the amount of charge as positive q. So we will be drawing twice the number of electric field lines entering negative 2q as is leaving q. Now this field is going to be influenced by each other. So I will just draw a couple representative field lines. I'm going to draw double the number of field lines from 2q as from q. So let's do another one. Might look something like this. I don't know for sure because I don't have my test charge probing. But let's say it looks something like that. Electric field lines leave positive charges and enter negative charges. So we now have 4 electric field lines leaving the positive Q charge, which means we should have 8 electric field lines entering the negative charge. And again, without my test charge, I'm only hypothesizing that the field might look something like this. And it would be disconnected from that positive Q charge. So now we're depicting 8 field lines entering the minus 2Q charge and 4 field lines leaving the Q charge, because once again, the negative 2Q charge has twice the number of electric field lines. And the extra 4 electric field lines will remain unconnected. They won't wrap around to the positive Q. Unlike the dipole on the left, all of those electric field lines will wrap around to connect because there is an equal amount of charge. So equal number of positive as negative charges. And that's not true for the charge configuration on the right. The value of the electric field at a point due to a charge Q is defined as the ratio of the electric force to charge that Q exerts on a positive test charge Q naught placed at that point. Now remember, as we discussed earlier, the SI unit for the electric field is the Newton per Coulomb. Let's take a look at this. So we have an electric field due to some source charge. Let's indicate that right here. Electric field due to some source charge. In other words, this electric field is caused by a charge. This charge cannot experience an electric force due to itself. All it's doing is communicating an electric field. In the absence of charges, remember, the electric field is a message in space saying, "Here I am." This depicts the electric field of a positive charge. This positive charge is our source. Now that electric field is directly proportional to the force that is exerted on our test charge in space. If we place our positive test charge right here, I will call this positive test charge Q naught. That positive test charge at that region of space lies along an electric field line. So it will experience an electric force that is repulsive. So this will represent the electric force at that region, at that point in space. And I'll just depict the electric field at that point as a small arrow next to it. So the electric force on that test charge is due to the electric field of our source charge. Let's indicate that here. Electric force on the test charge. And let's divide that by the amount of that test charge, Q naught. So this is the charge experiencing or under the influence of the electric field. The charge under the influence of the electric field. So you would say that the electric field is external to our source charge. We could rearrange this expression to say the electric force on charge Q naught is directly proportional to the electric field. And this is the way we normally express this relationship. We define the electric field as force per unit charge, but in practice, it's often more convenient to start our problems, to start our analysis by saying electric force is directly proportional to the product of the charge that's placed in an external electric field due to another source charge Q.